Example 5, we're going to have to pay close attention to detail. So the table shows domestic migration, so kind of moving around within the United States from 1995 to 2000. A person is randomly selected, and we're asked to find three different probabilities. So let's just zoom in on this and talk about this. For example, each of these numbers, it says it's in thousands, so it's really the 1537 is really 1,537 times 1,000, which would be 1,537,000. We're not going to worry about that. We're just going to use the numbers that we have as is. So looking at this, we've got 1,537 people that immigrated to the Northeast and 2,808 that emigrated from the Northeast. So they're moving around within the country. So the immigration is the people that are moving into those locations. The immigrants are the ones that are moving out of those locations. Now, the first question we're asked to find is what's the probability that an immigrant is from the West? Now, the way this is worded, this is saying that an immigrant, so that means just of the immigrants, of only the immigrants. So that means, in general, we're really just focusing only on this part here. So we're really just looking, what's the probability that they are from the West, assuming that we know that they emigrated. So in other words, we're going to do the total number of immigrants from the West divided by your total number of immigrants. Now, the number of immigrants from the West, that's just the 2654. And we're dividing that by your total number of immigrants. So we're going to have to add all those numbers up. Now, I've already done that, so I'm just going to skip ahead to 11,656. Now, folks, I'm not going to bother asking you to reduce that fraction. So what I'm just going to ask you to do is plug that into a calculator and get a decimal out of it. Now, I'm going to go 4 decimal places just because. It's a 0.2277. And if we convert that to a percent, that's 22.77%. So of all the immigrants, we know that 22.777 or 22.77% are from the West. Now the next one, it says, what's the probability, let me clear out some of this, sorry. What's the probability that someone from the South is an immigrant? So that means of just the total South. So that means we're just paying attention to all these folks. So the people that immigrated to the South or emigrated from the South. So again, we're going to say, what's the probability that of the people connected to the South, they're immigrant, assuming we already know that they're connected to the South. So it's going to be your number of immigrants to the South divided by your total number of the South. So the total number of immigrants from the South is that 5,042. And the total number of people connected to the South is, I already did this, it's 8,285. Again, decimals are great, so let's do 0.6086, got that from the calculator, which would be 60.86%. So 60.86% of the people that moved to and from the South were the immigrants to the South. The last one, it says, what's the probability that someone selected is both an immigrant and is from the Midwest? So we're not assuming that we know one category. So we're the probability of an immigrant and they're from the Midwest. So what we're going to do is do the total number of immigrants from the Midwest, so those that moved out of the Midwest, divided by the overall total. So we're just choosing somebody randomly from the entire population that we have here. And what's the probability that we randomly choose them and they are from the Midwest? So that's 2,951 divided by the grand total after adding them all up is 23,311. Now again, that's an annoying fraction, so let's reduce. Oh, I added too many ones there, sorry. Just put that as a decimal, that's 0.1266 or 12.66%. On example 6, we're going to take a look at decks of cards. If you're not familiar with them, there's a deck of cards has 52 cards. There's 4 suits. They are hearts, clubs, diamonds, and spades. And each of those suits has 13 cards. 52 divided by 4. So we're first of all asked to determine whether the events are dependent or independent. and then we'll find the probability. So the first one, it says, what's the probability of selecting a heart, replacing it, and then selecting another heart? So the word replacing is key here. So because you're replacing it, what you choose in the first one doesn't reduce the number of options you have for the second one. So it's independent. So the probability of a heart and another heart is just going to be the probability of drawing a heart times the probability of drawing a heart. Now, there are only 4 suits, again, hearts, clubs, diamonds, and spades, so the probability of drawing a heart is 1/4. For the next one, the probability of drawing a heart is, well, we didn't reduce the options. It's still 1/4. And so that gives us 1 out of 16. Now the second one says, what's the probability of drawing 2 queens without replacement? Since we are not replacing it, we're changing our options, so it is dependent. So the probability of a queen, then another queen, we're going to do what's the probability of drawing a queen times the probability of drawing a queen, assuming we already drew 1 queen. Now there are 4 queens. In this case, I'm going to just do this unreduced. There are 4 queens in a deck of cards out of the 52. Times, when we take a queen out, there is now 3 queens left out of a total of 51. Now thankfully, these both actually reduce pretty nicely. 4 out of 52, that's 1/13. 3 out of 51, that's 1 out of 17. Okay, they reduced a little bit. It's not perfect. It's not the worst, though. We can do this. 1 times 1 in our numerator is 1. 13 times 17, you can use the calculator for that, but that is 221. So if you're playing Texas Hold'em and you're drawing 2 cards, you have a 1 in 221 chance, assuming you're the only one drawing cards, of getting 2 queens. That seems really low, and it's crazy how often it actually happens. Example 7, a bag contains 10 beads, 2 black, 3 white, 3 red. We're asked to find the probability of drawing 3 red beads without replacement. So that means we're going to do the probability of a red, then another red, then another red. Which means we're going to do the probability of a red times the probability of drawing a red, assuming we already took one of the reds out, times the probability of drawing a third red, assuming we already drew 2 reds from there. Starting off, the probability of drawing a red, in fact, again, I'm going to recommend at first, don't reduce your fractions until the end. There's 5 reds out of a total of 10 beads. Times, now after you've already taken 1 red out, so this is the probability of a red, assuming we already took 1 red out, there's 4 reds left out of 9 total beads. Times, the last one, what's the probability of drawing 1 more red, assuming we already took out 2 reds? So that means there's only 3 reds left out of 8 total beads. From here, I would suggest reducing, so that way we don't have to do that whole, I mean, it's not the worst thing to do it, but 5 out of 10, that's 1/2. We already know that. Now for the rest of this, 4/9, that's not reducible, 3/8 is not reducible, but we can cross-reduce. So the 4 and the 8 we can reduce to 1 and 2. The 9 and the 3, we can divide both of those by 3, and we end up with 3 and a 1. So this ends up being way cleaner now. So in our numerator, we have 1 times 1 times 1, which is 1. In our denominator, we're left with 2 times 3 times 2, which is 12. Now again, if you didn't reduce it, our numerator would be 5 times 4 times 3, which gives us 60. And our denominator would be 10 times 9 times 8, which is 720. And you could reduce that to 1/12. So there's a 1 out of 12 chance that we draw 3 reds in a row.